Hi guys, this is Dr. Kato, Physics 100, Chapter 5, and we're just going to go through the diagrams that are in your current textbook. Okay, so I'm just going to read through this. This is the first one I think is very important, and it talks about the structures that are usually found when you find petroleum in the earth. So, formation of oil deposits in a geologic structure called an anticline, in which the rock layers have bent upward. The original forms in the source rock then migrate upward through the porous rock to collect in the top porous rock layer, where it's trapped by overlying impermeable rock. Natural gas may also be collected. So you need a lot of pieces for this to work. So this is kind of the soil and crust area here that built up after the rock was all bent into place. Then you have this impermeable cap rock here that nothing can go through, including water or oil, and that traps the gas and oil between this lower layer of porous rock, and then way down at the bottom you have the source rock that contains the original carrageen, which is the source of the petroleum material. So this source rock has organic algae and phytoplankton that has been trapped for millions of years, and the oil just sort of leaches out of this rock through the porous rock and collects in this layer over here. So a lot of things have to go right in order for you to discover oil. Okay, a couple of other important graphs that you should go back and review on your own. I'll just move this a little bit. Okay, this is figure 5.3. So this goes over a typical distribution of refinery products in the United States. The other category includes lubricants, asphalt, road oil, waxes, kerosene, solid fuels, and feedstocks for the manufacture of petrochemicals. The product mix varies with seasonal changes in demand. Okay, so other is a huge area. So under other is going to be all of the plastics that wind up in all of our bottles and cans and water bottles. So this is becoming a larger and larger area, right? And this type of material, once you make something into plastic, it's going to take millions of years for it to decay back into something that's can go back into the natural environment. So 47% of all of the petroleum that we take out of the earth in the United States winds up going to gasoline, 22% to fuel oil, so this would be diesel and home heating oil, 13% to propane and other gases, 8% to jet fuel, which is amazing because we drive around a lot more than we fly around, but yet this is a big percentage of this, right? This is almost a quarter of that, and I certainly don't fly every day, so it just shows you how much energy it takes to lift a jet off the ground. It is a very inefficient way of traveling in terms of energy usage. And then other, we said, winds up in all of these other materials like waxes and plastics. Okay, this is a really great diagram. We talked about it in the notes, so I won't go over it again. But you should definitely take a look at this, study it. There's a better version of it right in your new book references, okay, for chapter 5. Okay, so in the refinery process, right, we try not to do this too much, but a lot of times you'll be going past the refinery and you'll see them flaring off extra natural gas. So this is gas flaring at PetroChina's Tanzhou oil refinery. Well, this is nothing special about China. We do this in the United States. That's such a waste. We need to figure out ways to, rather than release this gas, to capture it and then use it for something productive. This is just burning, complete waste of gas. And you say, why would they ever do that? Because they're more interested in the petroleum, and they're just willing, in order to refine the petroleum, just willing to let the gas go off. Okay, but that really needs to be captured. Okay, it's a great diagram, figure 5.6. This is the world fossil fuel consumption since 1950. The height of each shaded area represents the amount for one of the three fuels. So this is coal, oil, and natural gas. So if you want to know how much natural gas was used in the year 2000, you have to measure from here to here. The amount of oil is from here to here. The amount of coal is from here to here. So you get a relative sense that the coal use has been going up. Then in 2000, it was kind of level from 1980 to 2000. Then it started to go back up again. That's probably mostly because of the fracking that's been going on. And we've sort of had a boom in coal as well. And again, look at the rest of the oil. The rest of the world uses a lot of coal compared to us. Oil's been going up. It went down. Here's the recession, the Great Recession. All three went down in 2008. Okay, so you can actually see that on the graph. That's pretty amazing. Okay, so that would be 2008. And you see we've been going up. Natural gas is probably going up a little bit faster than the other two, but they still are both growing, right? Okay, so that's world fossil fuel consumption. Okay, this is kind of cool. This is a comparison of natural gas, oil, and coal, and the number of kilograms of carbon dioxide you get for 1 gigajoule of energy delivered. So pound for pound for each amount of energy delivered. So all three cases, they deliver the same amount of energy. You can do the same amount of mechanical work with them, heat up homes. They would all be tied. But natural gas uses about 50 compared to 90 kilograms to create that 1 gigajoule. Oil would use 70 and coal would use 90. So on a percentage basis, this is almost half of this with the oil in between. And that has to do with the structure of the molecules that are making up the fossil fuel, right? Natural gas is made up of methane. There's 4 hydrogens for each carbon. Oil, the percentage of hydrogens to carbon is going to be lower than that, and coal is almost completely carbon. It's much more carbon than hydrogen. The hydrogen has been lost over the years, so it's mostly a carbon-based substance, whereas natural gas is more hydrogen in the structures of the molecules, and oil is someplace in between. So that's a huge difference when it comes to delivering greenhouse gases. For the same amount of energy, natural gas delivers about half the amount of carbon dioxide to the atmosphere. So it's much better to use natural gas than it is to use coal. Okay, this is a traditional power plant. I'll make it a little bit smaller for you. Okay, how's that? Okay, so this is a diagram of a typical fossil fuel power plant. So we've looked at diagrams like this before, but we can take a quick look at them again. You have, starts with a boiler, and inside that boiler you bring fuel in. So that fuel can either be natural gas if it's a coal-fired power plant, or it can be, in this case, if it's a natural gas-fired power plant, or in this case, if you're bringing coal in, you just bring tons and tons of coal in, and you burn it with air. So air and the fuel go in, ashes come out the bottom, and this flame's function is to heat up water that's running through these pipes. So inside this furnace, you just have this big chamber, and pipes are flowing through it. Okay? Why break it up into different areas? The more smaller pipes you have, the greater the surface area, so that the heat can get to the water that's inside the pipes. Gets boiled, and the water, and the steam comes out of this side. What happens to the exhaust from the burning of the fossil fuels? That goes straight out here through some kind of pollution control device to knock down all of the toxic ingredients, so that carbon dioxide, water vapor, and other gases come out the top. What you're really seeing more than anything is the water vapor from this combustion. Okay, but modern day power plants have a lot of different pollution control devices on them to try to keep the particulate for the most part, down so that the gas that's escaping is mostly just carbon dioxide and water vapor. Okay, so steam comes out here under high pressure, turns the turbine. The turbine is attached to a generator, which is a series of magnets that are wrapped in wire, and those wires generate electricity whenever you have charged particles or magnets that are rotating. You can create electricity. So this is a typical motor slash generator. In this case, it's being used as a generator. Okay, so the whole thing is designed to generate this power. That's the whole reason for doing it. Okay, on the other side of this turbine, you want to condense the steam so that the steam is being converted into liquid water in this series of heat exchangers that go down here. That will create this side to have a lower pressure than this side, and that's what keeps the wind going through this pipe to turn the turbine. If you don't condense this steam, the whole process will fall apart, right? You need to condense this back into liquid water so that you can run it through again. We don't just eject the steam into the air. That would be an open system, and we don't have anything like that anymore. Okay, so you essentially have heat exchange here and heat exchange here. Now there's a secondary group of water that comes from a lake or a river up into this box. That cool water is cooling off those pipes to condense the steam into water. And then it flows back out much hotter than it went in. We don't want to dump it directly into the lake so hot. So what do? We put it through a cooling tower first so that the air cools it down, and then we drop it into a lake at just a few degrees warmer than it went in. Okay? In fact, in a perfect scenario, the cooling tower would completely cool it off so that we were putting it back into the river at exactly the same temperature. But as long as it's within a few degrees, you're okay. You cannot be dumping hot water into a lake or a river, because that hot water will kill all of the fish. The water heats up, there's going to be that much less oxygen, and basically the fish would suffocate. And they would be replaced by organisms that like it hot, and so the algae would bloom in a lake or river, and that's the last thing that we want to happen. Okay, so that's one. Figure 5.9 you should definitely go over. Okay, before I move on to talk about internal combustion engines, I just want to spend a little time on this system. This is a more advanced called a combined power cycle power plant. So the diagram for a combined power cycle power plant, the steam cycle is similar to the one illustrated in a traditional plant that we just saw, although the details of the cooling and exhaust system aren't shown. Hot gases from the gas turbine replace burning the fuel in a steam box. Okay, so we have two things that are going on. Okay, so the first thing that you do is you have a combustion chamber up here where you put the fuel in. Probably in this case, the details aren't showed, but that combustion chamber, this is probably natural gas and air, and they're being burned in this chamber. Okay, so here comes the air. It gets compressed and filtered and compressed, mixes with the fuel. Okay, if it's burning, it's creating a lot of pressure, can't go back out this way, so it's forced. This hot exhaust gas comes through here and turns the turbine. The hot gas comes down into here, is cooled down. If this is much colder than this compressed gas over here, you have a pressure difference where this is the low pressure side and this is the high pressure side. If you have that, you'll create a constant flow of wind that's going through it that's going to turn the turbine and therefore turn the generator to generate electricity. So we're able to get generation over here, but now this hot exhaust gas still has a lot of heat content. So why not run a heat exchanger through that hot gas before it escapes to cool it down? So when you cool it down, you're able to capture some of that heat in this series of pipes so that the cooler water gets converted into steam in this section, and that boiling water comes down this side. It's steam, I should say, that boiled steam, high pressure, gets condensed on this side into liquid water. So again, this side is high pressure, this side is low pressure. You have a constant wind that's going to turn this turbine and generate electricity. So you can generate electricity twice, right? So you can extract that much more mechanical energy. You take it first, you take the mechanical energy from the pressure in the actual combustion reaction, in the burning process. And then you take the heat using a typical heat exchange system and boil water like you did back on the diagram a few pages back. So you basically wind up with more electric power. I won't say necessarily twice as much, but this is much more efficient because of these two processes than this one was. Back here, right? So that's the difference between a traditional power plant, 5.9, and 5.15. Much more efficient. It's called a combined cycle power plant. Okay. Here's some of the coal reserves that are found in the world. So this is total coal reserves. This is in gigatons. So if you look at North America, and including the United States, has one of the largest reserves in the whole world. Asia and the Middle East are much smaller. So the difference between the two colors, I'll tell you in a second, is world coal reserves in gigatons, billions of metric tons. The full height of each bar gives the total coal reserves for the indicated continent, while the lower part shows reserves that of the listed country. So this is the total, where most of it turns out to be in the United States. So for North America, Canada and Mexico only have a little bit of the coal, and the United States has most. So that's a good thing for us. Central and South America, Colombia has the most coal reserve, right? It's the bottom bar there. But again, very little. Western Europe, where Germany has the biggest coal reserves. Russia, Eastern Europe or Eurasia, where it's mostly Russia. Africa, where it's almost entirely South Africa that has the coal reserves. And Asia and the Middle East, including China, where China has has this big chunk here, but this represents the whole thing. So the United States has more than China, and almost as much as this whole bar, which is Asia and the Middle East. So again, this is coal reserves, not necessarily oil reserves. Okay, here's the oil reserves, and again, they did it the same way. Okay, so this time we're not so lucky. So these are world oil reserves presented as for coal in figure 5.16, with the Middle East broken out separately. Data for North America includes tight oil access through hydraulic fracturing, as well as Canadian tar sands. So that's probably one of the reasons why this is so big over here. So first thing, Middle East, including Saudi Arabia down at the bottom, has the most oil reserves in the world, much more than anybody else. Okay. Central and South America is second, with Venezuela, which you know. They're going through a lot of political turmoil right now, and it's partly because of the oil reserves that they have. So Venezuela has a huge oil reserve. United States, this is, North America, so this is Canada, the United States, and Mexico, where Canada has the most, and probably because most of it is locked up in the oil sands. But again, there's a lot of oil in Alaska and a lot of oil in Western Canada, in the Yukon and Alberta and Calgary. That's one of the reasons why those places are boom towns. Here's Europe. Almost all of it is, not much, but almost all of it in Norway, and that's usually off the coast of Norway. That's called in the North Sea. Okay, here's Eastern Europe, mostly Russia. Here's Africa, mostly Liberia. The other African country that has oil is Nigeria. And then here's Asia and Oceania, which is all those tiny islands in the Indian Ocean and the Pacific, and with China having the biggest reserves here. But again, Saudi Arabia, just by itself, has more than all of North America. And here's the whole Middle East. So they definitely, by far, have the most oil reserves. Okay. This is U.S. oil imports rose substantially in the 20th century to compensate for declining domestic production. A dramatic turnaround occurred in the 21st century as the result of increased domestic production associated with hydraulic fracking. So this is hydraulic fracking that goes on mostly in New York and Pennsylvania. So let's take a look at this. This is total domestic production here till you got to about 2010, and then look how much we went up. It would be very interesting to see. This gets you to about 2015. And then here's how much oil we imported, where we had a maximum, right, in the oil embargo of about 1975, and then that dropped off dramatically. And then we kind of came back through. And this peak right here would also correspond to about 2008. Okay. Here's an offshore oil rig. So huge structures, right? Built onto the where basically you're drilling. Not only you're going down thousands of feet through the water, and then you're going and you're starting to drill into the bottom of the ocean underneath. Okay, so offshore drilling rigs produce some 30% of the world's oil. Okay, Gulf of Mexico, and we said off the coast of Newfoundland in the North Atlantic, and off the coast of Norway in the North Sea. World's reserves of natural gas. Presented as for oil in figure 517. So again, the total for this continent and the largest country underneath. So for natural gas, the United States has most of the natural gas of the three countries that are in North America. Natural gas, again, Venezuela leads South America. Europe, Norway leads all of Europe. Again, this is the gas that's collected with the oil in the North Sea. And Eastern Europe, mostly Russia has a huge natural gas reserve that they sell to Europe. So Russia makes up most of Eastern Europe. Here's Africa with Nigeria being the biggest producer of all. Here's Asia with China being the biggest producer of natural gas. And here's the Middle East with the tiny country of Qatar being the having the largest share of any of the other countries involved. Okay. This is a diagram of what actually has to happen in terms of a fracking system. So once the traditional oil is all pumped out of these kinds of places, you can go back and collect extra gas and oil in some cases by doing this process. So let me read through it, and we'll talk about the oil derrick again. At the surface, there's a groundwater table. So this is a permeous rock that's been saturated with water from the rain that has created it, and this is the water that people in these areas here drill into in order to get their drinking water. Then there's some kinds of overlying rock layers that are somewhat impervious, and then another impermeable solid rock that's called shale. So inside this huge amount of shale rock, you basically pump liquids, water, chemicals, and abrasive materials into the rock to kind of force out or push in and make gaps in the rocks. Sorry about that, my computer got shut off. And then what happens is you force those gaps into the rock, force the gases and liquids of petroleum to seep up through the surface, and they're collected in another well. So if you have the fracking well and then a collection well. So this is a typical fracking operation. Begins with a vertical shaft sunk into the impermeable shale. Horizontal drilling, which means drilling across, extends the well through the shale formation. Water pumped in at high pressure creates fractures in the shale, allowing oil and gas to flow into the well. In a typical operation, multiple horizontal runs would extend from a single vertical shaft. So you could have one going this way, one going this way, one going that way. I could kind of draw how that would look. So rather than just being one pipe that comes down into the shale, you could have one coming off this way, one going off this way, then one even deeper. So they basically have some way, I don't know how they do it, but they basically drill sideways and put all this liquid and pressure that pushes the oil and gas up, and that's what you want to collect. Okay. And then the last thing I think that's in here for the chapter is this is a picture of liquid oil can be extracted from the tar sand. So here's tar sand in somebody's hand from Alberta, Canada. It takes 2 tons, so 2,000 pounds of sand, okay, of this oily sand to make a single barrel of oil. And a barrel of oil is like 42 gallons of oil, so it's not a lot, okay? Something like that, like about 50 gallons of oil. That is a lot of extraction that you have to do to make 1 barrel of oil out of 2 tons of this tar sand. And again, it takes a lot of energy, it takes a lot of steam to push through this material to get the gas, to get the oil off of the tar so that you can use it. Okay, here's one of the backhoe kinds of devices that they use to pick up the tar sands to bring them to these mega factories, and you can just see the size of this digging device. So it takes 2 tons of sand to make oil. The shovel, so this mechanical shovel here, suggests the enormous scale of tar sand extraction process that's going on in Western Canada. Okay, this is called Herbert's curve. Okay, let me read through it first, and then we can talk about it. So figure 5.24, an idealized bell-shaped curve for oil production illustrates Herbert's peak. Production peaks when half the resources have been extracted. Thereafter, the production rate declines as the remaining oil reserves become more difficult and expensive to extract. So you can move up and extract it until about half of all the oil has been removed. And then this second half is a lot harder to get out of the earth than the easy first half. So we're starting to move in, I'm going to show you on the next page, to the back half of this curve. So this is about 1900 when we started to take oil out of the ground at a big rate, and here we are in 2020. So the rest of the way is going to be a lot harder than getting the easy stuff. We already got the easy stuff back in the day. Here's the real curve of what we're doing, of the amount of material that's been extracted. Sorry. A sophisticated mathematical projection of world production has the peak occurring in 2021, which this is 2020 right now, so we're pretty much at the peak. This particular projection assumes an ultimate reserve of 3 billion barrels, nearly twice current estimates. Black dots represent actual data. The solid curve is the model projection of where we're going from there. Again, we were on a bigger trajectory before 1975 and the oil embargo, and then we dropped back off. But we kind of almost picked up where we left off. Like if you close this and we would have never done anything, you could see we'd almost be in the same place, right? But this is a lot of oil that we never took out of the ground yet, so it's kind of still there to be taken. So that's kind of a good thing that we backed it off a little bit. But we kind of went right back since about 75 when we dropped down. We kind of picked up back where we left off to catch up with this natural curve. Okay, I think that's it. That's what I'm going to talk about from that chapter. The only thing I did not talk about, and I'll save it for a different video, is there's about 4 or 5 good diagrams related to internal combustion engines. So I will spend some time on that, and I'll load a couple of professional videos on how an automobile engine works. So that'll be the last video for Chapter 5. Okay, guys, thanks. Talk to you soon.